Hello, my name is Brendan, and I'll be presenting unsupervised learning of probably symmetric deformable 3D objects from images in the wild by Wu, Rupprecht, and Vedaldi. Today, the majority of existing learning-based approaches to 3D reconstruction are supervised. However, the authors of this paper aim to solve 3D reconstruction from images under two new major constraints. The first of which is that no 2D or 3D ground truth information is available. And the second is that the model will only use single-view images, no multi-view inputs. This is in accordance with the in the wild theme of the paper. Performing 3D reconstruction from an image in an unsupervised setting is more usable than the previous supervised reconstruction efforts. It makes the algorithm a lot more accessible to industry. One major challenge, though, is that there's a low quantity of research for 3D reconstruction in an unsupervised setting. The authors of this paper are establishing a lot of the groundwork in the area. Featured on the center of this slide is a table containing many of the seminal prior works on the topic of 3D reconstruction from images. The majority of the prior works contain additional inputs to the model, like 3D morphable meshes, as well as supervisory signals, like 2D key points, 3D points, and 2D silhouettes. The few completely unsupervised prior works don't have source code or they don't have quantitative results. The methods used in the completely unsupervised approaches were dominated by GANs and autoencoders. The authors propose an unsupervised autoencoder approach to 3D reconstruction from images. Their autoencoder approach will factor each input image into depth, albedo, viewpoint, and illumination without ground truth. This approach is ill-posed without additional constraints. There are many combinations of depth, albedo, and viewpoint and illumination that can generate roughly a similar-looking image. So the authors introduced some additional assumptions, such as taking advantage of bilateral symmetry in objects, such as the human face. This is one of the first works in unsupervised 3D reconstruction to show strong qualitative and quantitative results. The model takes into account that most objects are not totally symmetric by predicting a confidence of symmetry for each pixel, which is very novel when compared to previous approaches. Qualitatively, the results look much better than the prior works. The depth maps look very good even when rotated to different viewpoint transformations than the original image. Additionally, many of the hairline features and jaw features are retained, unlike some of the previous autoencoder approaches. The author's main goal is to implement a neural network that will decompose an input image into 4 variables: depth, albedo, viewpoint, and illumination. The authors use a reconstruction learning objective, where a reconstructed image is created from the 4 variables. This is formulated as first a lambda function of the albedo, depth, and illumination, which computes a canonical view of the predicted depth map. This canonical view of the predicted depth map is then warped using the depth and viewpoint into the pose of the original image and then projected back down to 2D. This is the image reconstruction known as I-hat. The authors incorporate their bilateral symmetry assumptions by performing a second reconstruction, I-hat prime, where the albedo and depth are flipped along the horizontal channel. To account for the asymmetry in images, the authors predict a confidence map, sigma. A visualization of the confidence map is overlaid on a sample image where the red regions correspond to asymmetry and the blue regions to symmetry. The primary loss function is the negative log likelihood of the factorized Laplacian distribution, where the variable is the L1 distance metric at spatial coordinate uv between the image reconstruction I-hat and the original image I. Now, the authors note that this loss leads to blurry reconstructions, so in order to increase the visual fidelity, the authors also compute an embedding for the image reconstructions, I-hat and I-hat prime, as well as the original image I. The way these embeddings are computed is they take an encoder network like ResNet or VGG, put the image through, and take the output of the kth layer to be the embedding. An L1 distance is calculated between the embeddings of the reconstructions and the original images, and this L1 distance metric is used as the variable of the negative log likelihood of a Gaussian distribution, which is titled the perceptual loss. The authors update the loss definition to then include both the original L1 distance-based loss that we just spoke of, as well as this perceptual loss. And these two losses are calculated for both the image reconstruction I hat as well as I hat prime, where the latter two losses are weighed slightly less at 0.5. With the four-factored variables, the method is as follows. First, the canonical depth map, J, is calculated as an output of a lambda function of the albedo, depth, and illumination. This J variable is the canonical depth map at viewpoint W equals the 0 vector. Essentially, it's the head-on view of the 3D representation of the input image. Then, a reprojection function pi is calculated using the canonical depth map, depth, and viewpoint. Essentially, what this reprojection function does is it warps the canonical depth map to the pose of the original input image and then projects it to 2D to obtain the reconstructed image. The figure on this slide provides an illustration into how the model functions. Encoder-decoder and encoder networks predict the confidence, view, depth, illumination, and albedo from the input image. The lower right corner of the figure corresponds to the lambda function that we previously spoke of, the output of which is the canonical view J. This is just an analytical function which is computed at runtime. Using the canonical view J, the depth, and the viewpoint, the renderer produces the reconstruction I hat, as well as the reconstruction I hat prime for the flipped depth D prime and albedo A prime. Now these reconstructions I hat and I hat prime, along with the confidence maps sigma and sigma prime, are used to compute the reconstruction loss for each input image I. To evaluate the performance of the model, the authors introduced the scale invariant depth error metric based on these delta UV variables. Now each delta UV is the difference of the log of the predicted depth map for a spatial coordinate pair UV minus the log of the ground truth depth map at spatial coordinate UV. The side is then the standard deviation over all of the delta UVs. The authors also look at the mean angle deviation between normals computed between the ground truth depth and the predicted depth. And the MAD helps quantify how well the surface details are captured. Experiments were performed using the Basel face model dataset, which is a synthetic dataset of faces with ground truth depth maps. The authors compared the unsupervised variant in the model that we just discussed versus a supervised variant, as well as several baselines based on the constant null depth or the average ground truth depth. Now, the side and MAD metrics, where lower corresponds to a better score, are a little bit better for the supervised model. However, the unsupervised variant approaches the supervised variant scores and is much better than the constant null depth and average ground truth depth baselines. Qualitative results can be seen in the right figure, where the canonical view J corresponds to the center column. To justify the inclusion of various features, the authors performed an ablation study. The most important features were determined to be the explicit modeling of the illumination as well as the albedo flip. As can be seen qualitatively on the left, without the explicit modeling of the illumination, the normals, shading, and albedo look very poor. Quantitatively, including the confidence maps didn't have a large impact on the side or MAD. However, the Basel face model is a face data set, so there's a lot of bilateral symmetry. To justify the confidence maps, the authors came up with a perturbation experiment, for which they placed colored squares randomly on the image. The reconstructions without the confidence actually ends up replicating the colored square on both sides of the image, whereas the confidence reconstruction only has the colored square on a single side of the image, and the quantitative scores reflect how important the confidence is for perturbed images. The authors also compare their unsupervised model to many supervised models on the 3D faceline in the wild dataset. This dataset is composed of face images as well as 66 key points, each of which has a ground truth depth value. To evaluate the performance on this data set, the depth correlation score is used. Depth correlation values range between 0 and 66, and they are computed as the sum of the absolute value of the correlation between the predicted depths at a key point and the ground truth depths at a key point. The unsupervised model that the authors have introduced in this paper performs better than most of the supervised 3D reconstruction models, and is only worse in terms of performance compared to DepthNet GAN on this data set. The model introduced in this paper was found to be competitive with supervised models on various face datasets. Qualitatively, the model performed much better than previous unsupervised works, and the authors have shown that symmetry and illumination are strong cues for shape and aid the model in predictive ability. The author acknowledges that the model has several limitations due to architecture design, and these limitations include extreme lighting, noisy texture, and extreme pose. One critique is that the authors could have provided a bit more information on confidence maps, since it's one of the more novel contributions for modeling asymmetry. Additionally, the model does not output a full 3D mesh, but a depth map, which might not be enough for some use cases. Another paper has discussed how the model also only works for images with a single subject and doesn't work for multiple subjects. To recap, the authors introduced a new model for 3D reconstruction from images that's unsupervised. Prior works had been supervised with things like ground truth meshes and silhouettes. This work can exceed some supervised models in performance, and the model uses encoder-decoder networks to extract 4 variables: depth, albedo, viewpoint, and illumination. For asymmetrical inputs, the confidence of symmetry was the key.